Homework 3.1, Quadratic Functions, Video 1. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. All right, time to start the material that'll be on test 3, which, by the way, will be available on Monday, May 25th and be due at 11:59 p.m. on Wednesday, May 27th. This test will cover 5 homework sections, so it has fewer sections on it than test 2 did. All right, so in this section, we're going to talk about quadratic functions. Now, those are 2 words that we've tossed around quite a bit already. We've talked about functions quite a bit in chapter 2. Test 2 had a lot of functions on it. F of x equals. We talked about graphing them, and we talked about various other things as well. And we've also talked about the word quadratic quite a bit, and that was more on test 1 when we solved quadratic equations using a variety of techniques. Just a reminder that the word quadratic means that the highest power is 2, or equivalently, that the degree of the polynomial is 2. As we'll formally define in the next section, degree is the highest power in a polynomial function. But we already know some things about graphs of quadratic functions. Based on what we saw in section, I want to say it was 2.1, homework 2.1, we learned, or rather reviewed, that quadratic functions graphs are parabolas. So either they open up like this, or they open down like this. And if you're wondering, can they open to the left or to the right? Well, not if it's a function, because it would fail the vertical line test, but there are equations of parabolas that would open left and right instead of up and down. Basically, if the y is squared and not the x, then it opens left or right. But since we're discussing functions, we are not going to run into those. All right. So if we're going to graph parabolas, a very useful piece of information to locate would be the low point or the high point where the parabola turns around. For example, on this parabola that opens up, there's a point on the bottom that we could call a minimum, because the word minimum refers to the y value. So if this were living on a coordinate plane, this point would have the minimum y value on the whole graph. But if it's a parabola that opens upside down, then the turning point would actually be a maximum, meaning that this is the maximum y value on this whole graph. But regardless of whether it's a minimum or a maximum, the point where a parabola turns around is called the vertex. So both of these are vertices, which is the plural of vertex, V-E-R-T-I-C-E-S. Vertices is the plural of vertex. So we're going to try to predict, before we graph a function's parabola, if it's a quadratic function, whether the vertex will be, well, first off, where the vertex is, and then whether it's going to be a minimum point or a maximum point. Now, the answer to minimum or maximum is really easy, and I think you may already know this. The graph of y equals x squared is your standard parabola that opens upwards. But what can we do to that function to turn the parabola upside down? I think some of you already know that sticking a negative in front of the x squared would cause it to turn upside down. So where in these 2 examples would we look to determine whether the parabola opens up or opens down? Well, these aren't written in general form, if you will, but rather standard form. Both names I hate. This one would be called standard form. If you'll recall from the discussion about equations of lines, general form is usually the one that has no parentheses and everything's all just sitting there. This one has some parentheses. We'll call this one standard form. But if we have a quadratic function in standard form, it looks like some number times the square of x minus a number, or it could be x plus a number. Right now that number is generically being represented with the letter h. And then there may be a number added or subtracted at the end. But in terms of where do we look to see if this parabola opens up or opens down, the answer is it's the number in front of the x squared. Well, the x squared is kind of hidden in here because we would have to write this parentheses out twice and FOIL it, and then distribute the number in front, but it's this number in front that would show up on the x squared, so it's still this number in front that determines maximum or minimum. So before we go tracking down a vertex, let's go ahead and nail that. If the leading coefficient a is greater than 0, then your parabola opens up. And if your leading coefficient a is less than 0, then your parabola opens down. If you're positive, you're smiling. If you're negative, you're frowning. It's a cheesy gimmick, but if it works, it works. So right at the gate, we can identify if the parabola opens up or down, and as a consequence, identify whether or not its vertex is a minimum or its vertex is a maximum. For example, in this one, f of x equals 2 times the quantity x minus 3 squared plus 1. Because the leading coefficient will be 2, and that's greater than 0, we already know that this parabola is going to open up, and therefore the vertex will represent a minimum, as opposed to this one, f of x equals negative quantity x plus 2 squared minus 4. The leading coefficient on this one would be negative 1, which is clearly negative, and therefore we know that this parabola would open down, and its vertex would represent a maximum. So it's easy to identify open up or open down, and as a direct consequence, is the vertex a minimum low point or a maximum high point? But we still haven't actually located where the vertex is. So let's think about this, and then from our results, we'll extract a quick way to get the vertex. We know that this first function, because the parabola opens up, will have a minimum point, a low point. So let's think about what we could do to make this expression return the smallest possible value. Now the plus 1's going to sit there and nothing's going to change yet. And this is a 2, that's still waiting for something to happen. The only thing we can really control is what's inside this parentheses, and it's getting squared. So let's just get rid of the 2 and the plus 1 for a second. Don't worry, I'll put them back. In order to crank out the smallest possible value, we're going to have to make this the smallest possible value, because whatever it is going to get doubled and then have 1 added to it. So what's the smallest possible value we can make here? And keep in mind that we're squaring things. Well, if x minus 3 is positive, then when I square it, it's positive. But if x minus 3 is negative, then when I square it, it also comes out positive. Is there any way that this result can come out negative without using imaginary numbers? No. But is there any way that this squared parentheses can come out to be 0? Yeah. If this parentheses can end up equaling 0, that's the smallest value I can make it. Think about the parabola that sits on the origin, f of x equals x squared. The smallest value it can obtain is 0. So it doesn't really matter what's inside of there. The smallest value I can get from squaring something is 0. Let me bring in the 2 and the plus 1. All right, so to figure out where the bottom of this parabola would be, we need to choose the x that would make this squared parentheses as small as possible. And we know that the smallest possible value of anything squared is 0. So it boils down to what number can I substitute for the x so that the subtraction problem is equal to 0? Well, that's easy. What minus 3 equals 0? 3 minus 3 equals 0. So it kind of makes sense that the vertex is at x equals 3 because that'll give us the smallest value, not only with the squared parentheses, but for the result, and hence the minimum y value. But x equals 3 is only half of an ordered pair. A vertex is a point. Something comma something. Well, we're claiming that the vertex is going to be at x equals 3, but where would its y coordinate be? Well, we know how to get a y value out of a function. Stick in an x value. The y value would be f of 3, but we can talk this one out pretty straightforward. If I put 3 here, 3 minus 3 is 0, 0 squared is still 0, 2 times 0 is still 0, and then finally plus 1. So the vertex is at 3, 1. This x value will produce the lowest possible y value, and hence give us the lowest point on the graph. And we can do the same thing for a graph when it's upside down. Well, I should say opens down. Who's to say that this one is right side up and this one is upside down? But if it opens down, then the vertex doesn't represent the lowest value, it represents the highest value. So this one takes a little bit more thinking, and we'll put the -4 back in there. Actually, we'll leave it there just for a minute. If I want this to come out as large as possible, then I need to make this parentheses squared as small as possible. Why? Because I have a negative on it. If this parentheses were to get larger and square it and get even larger and then stick a negative on it, it's going to drag the value further and further down. But we need the maximum possible value. So in order to get the maximum value out of this, we actually need the smallest possible result of squaring something because it has a negative on it. Gee, this sounds exactly like what we did over there. So let's see if we can figure out where the vertex is at. Vertex is at x equals. Again, even though we're trying to get the largest possible value, we need to make this as small as possible because it's negative. It's like saying if you want the largest bank account, but you have to write a check, then you want to write the smallest possible check to keep your account as large as possible. So, if we want this to be as small as possible, we need x plus 2 to equal 0 again. So what value would make this addition problem equal to 0? -2. And where would that put the y coordinate? Well, whatever we get when we substitute -2. Well, -2 plus 2 is 0. 0 squared is 0. -0 is still 0. And then -4 is -4. So it looks like this vertex is going to be at -2, -4, representing a maximum point. Now, these two graphs live on separate coordinate planes, but don't let that bother you. Because why is this one on the same horizontal? Anyway, I'll get off that tangent. All right, so what's really going on here? What's the fastest way we can say here's the vertex? Well, you can tell I've already got it set up. Let's think about where we can look to find the x-coordinate. The x-coordinate here was 3, and that was what was being subtracted. But that looks like a -3 there. The x-coordinate here was -2, but what I see there is a +2. You know what? Let's go back up to this one and double underline the sign as well. For the x-coordinate, what seems to be happening when we take the number from here to here? Well, it looks like a -3, and this is a +3. This looks like a +2, and it comes out a -2. So whatever number is here, we have to change its sign. So if I write x minus h, then the x-coordinate of the vertex would be +h. Well, what about the y-coordinate? The y-coordinate here was 1, +1, and +1 is what was at the end. And the y-coordinate here was -4, and -4 is what was at the end. So it looks like the y-coordinate is whatever number is sitting at the end. So you don't change its sign. So to pull out the vertex from standard form, you look after the x, you change the sign, and then you grab the number at the end and you keep the sign. But if you understand why that both the minimum and maximum occur when we can make this parentheses equal to 0, hence the opposite signed number there, then we just get this result. So the same signed number. We'll see more instances of pulling the vertex out of a quadratic function in standard form, but it's really quite easy. Just change this number sign and keep that number sign. Oh, that's way too long for the first video. Oh well.